Hello everyone, myself Dr Pradeepa S M, working as an assistant professor in Department of Chemistry at RNS Institute of Technology. Right? So now I am here to explain one of the very important experiment which is coming in our chemistry subject, and this is the experiment. So that is estimation of iron in TMT bar by external indicator method. Before going to understand the actual experiment, now let us discuss something about the one more word, that is TMT, right? That is TMT. So what is the full form of this word TMT? These are thermomechanically treated bars. The TMT long form is these are thermomechanically treated bars. So these bars are the most widely used and most essential and widely used bars for almost all kinds of construction purposes. These TMT bars are highly ductile. These TMT bars are highly ductile, allowing them to withstand the seismic forces, right, better than these conventional or traditional steel bars, right. So that's why these particular property of the TMT bar, so they are suitable candidates for the construction of earthquake resistance buildings, right, ensuring the safety of the occupants and reducing the risk of structural damage to the buildings during seismic events. Usually you might have seen this Indus TMT. Most commonly every day in the advertisement you are seeing these TMT bars. So they will be rating iron 550D, right? Iron 550D TMT bars. So what is the meaning of this word iron TMT 550D TMT bars, right? So if you can look, this Fe is it refers the iron content of the bar, and this 550 is the minimum yield strength of the bar, and D is the ductility. Now let us understand the principle of this experiment, how one can determine the amount of iron present in this TMT bars, right? So we know that one of the most common source of this iron in order to manufacturing these TMT bars is hematite ore, right? So iron ores are, so many ores are there, like hematite, magnetite, siderite, pyrite, etc. So out of that, hematite is the most common ore. So using that, this is the source, and the structure is again Fe2O3. So this is the thing, right? So this hematite ore consisting of a small amount of silica and other impurities. So that's why, so in this experiment, so first of all, we are going to treat this TMT bar or this ore or the solution which consisting of iron is treated with concentrated HCl, right? That is called as the digested, right? It is digested with concentrated HCl. So thereby it is going to form ferric chloride. It is going to form ferric chloride, right? So this ferric chloride, it is diluted and filtered in order to separate it from silica and other impurities, because hematite ore may consisting of silica and other impurities, right? See, whatever the ferric chloride which is obtained, in this ferric chloride, iron will be in +3 oxidation state. Iron will be in +3 oxidation state. So +3 oxidation state is the highest oxidation state of this metal iron, right? So we cannot oxidize further. So that's why it is not possible to treat this ferric chloride straight away with potassium dichromate. Because it cannot be further oxidized. So that's why we are going to treat this with stannous chloride. So that we will reduce this ferric chloride in the first step, and then in the second step we are going to oxidize, right? Whatever it may be, we want the amount of iron present in the TMT bar solution, right? So that's why this ferric chloride is treated with the stannous chloride. First, in the first step, it is reduced by treating with stannous chloride. Stannous chloride is one of the very strong reducing agent, right? If you treat this ferric chloride stannous chloride, ferric chloride is converted into ferrous chloride. That means iron will be converted from Fe3 plus oxidation state to Fe2 plus oxidation state. Right? And the stannous chloride is converted to stannic chloride. Right? It is soluble in water, it can be easily removed. So now, actually after this step, so we are going to add 2 more drops of stannous chloride in order to ensure complete reduction. Right? So no ferric ion should be left in the solution. So everything should be converted into ferrous. Right? So as we have added a little excess amount of stannous chloride, it should be destroyed. Right? It should not be there in the solution. I will explain the reason when giving the demo. So anyhow, so if in order to destroy this excess stannous chloride, we have to treat this with mercury chloride. Right? If you treat this stannous chloride with mercury chloride, it will destroy the stannous chloride and convert into stannic chloride, and this mercury chloride is converted into soil as mercurous chloride, and this itself is a silky white PPT. Right? We have beautiful silky white PPT is going to get in the solution is because of the formation of solid mercurous chloride, that is Hg2Cl. Right? So it will be a precipitate, white precipitate. So then after this we have to treat this ferric chloride with potassium dichromate. We are going to do titration against the standard potassium dichromate solution. It is an oxidizing agent, so that's why when you treat this ferric chloride, ferrous chloride with potassium dichromate solution in presence of acid or in acidic condition, it undergo simultaneous oxidation reduction reaction in this way. So that will be converted into ferric chloride. Right? From ferrous chloride is converted to ferric chloride. So again, iron is converted from Fe2 plus to here it is Fe2 plus. It is converted into Fe3 plus. And simultaneous reduction is also going to take place. Potassium dichromate chromium will be in plus 6 oxidation state in the beginning. After the oxidation process, it will turn to plus 3 oxidation state. So that means the potassium dichromate while oxidizing this, it undergo reduction by itself. Right? So this will be taking place. So here we are going to take potassium ferricyanide, that is K3FeCN6 is used as an external indicator in order to detect the end point. Right? It is used as an external indicator. The name of this is potassium ferricyanide. Right? So overall, in this experiment, unlike all other conventional titrations, here we are not using internal indicator, we are using external indicator. There is one difference. The other difference is, unlike all other titrations, here there is no change in the color of the indicator is the end point. Right? Whereas in all other titrations, there is a change in the color of the indicator is the end point. Here there is no change in the color of the indicator is the end point. Right? So this is all about the principle of this experiment. So now let us see the demo of this experiment. I will give a demo of one can perform this experiment. So as I already mentioned, there are 2 steps in this experiment. The first step is the preparation of standard K2Cl2O7 solution. So in order to prepare that, you have to wash the standard flask and funnel and come along with your manual. So here they will be keeping this K2Cl2O7 crystals. So you have to take the salt weight. So first is you just carefully you can place it on the pan like this, and it will show the weight of weighing bottle plus salt, and that will be 4.944 gram. Right? So this will be M1. So you can write this 4.9446 gram. Right? So now you have to carefully take this out and transfer through this funnel into this 250 ml standard flask. Okay, and just tap like this, and then take the weight of the empty weighing bottle, right, and in the same way, and note down the M2 weight, and that will be 3.685, right. So and then keep this outside, and then you have to go for adding distilled water through this funnel in the beginning, and you have to add distilled water stepwise, and you need to make up the mark. So for that, let us go to the table. So we need to add distilled water through this funnel for the first 2 to 3 times, right? it will take time like this. So first add through the funnel. Okay, so 2 to 3 times you can add, and then you can remove this funnel and add the water through the walls of the standard flask like this. Okay, so step by step you can add water and stir the solution because it will be dissolved very quickly, no problem. So up to this neck of the standard flask only you have to add using water. So the remaining small portion should be filled by taking water in the burette. See, I have taken a small amount of water in the burette. So now I am going to add and make up to this mark. Mark is here. After making up to this mark, so you have to close this lid, right? And you have to shake this solution by keeping invertedly like this. So if you do like this by invertedly stirring this, it will be uniformly dissolved. So like this you will do 4 to 5 times. It is sufficient and it will be completely dissolved. Now remove the lid and then discard this water which is taken in the burette and fill the standard solution, that is K2CO2 into the burette. So before filling you have to rinse this burette with standard K2CO2 solution. So now I have prepared the standard K2CO2 solution and I have filled it with the burette, right? So this completes the first step. So now let us move towards the second step, that is titration step. So the chemicals which are required to do titration are, so one is TMT bar solution we want, the other one is dilute HCl, that is hydrochloric acid, we need to add 1/3 test tube, and this is stannous chloride is a strong reducing agent, we need to add this dropwise into the reaction mixture in hard condition, and then we want mercury chloride in order to destroy excess stannous chloride, and this is a beaker we need to collect from the storeroom. So in this beaker you have to take tap water and there will be one test tube which consisting of distilled water and a glass rod, right? So and along with this we want the indicator, that is potassium ferricyanide. It is an external indicator. Okay, so now by keeping all these reagents or chemicals, now I have prepared out 25 ml of TMT bar solution. So to this what I need to add? We need to add 1/3 test tube of dilute HCl in order to digest this TMT bar solution. So I will add 1/3 test tube of HCl. So very carefully I will add because it is acid. Okay. Take exactly 1/3 test tube. It is up to this rubber mark you have to take. Then you need to add it to the solution. Okay. So after adding this HCl, right, you need to heat the solution until it starts boiling, right? Because stannous chloride should be added in the hot condition. Now let us go for heating the solution. This is the electric stove. So on which only we are going to place this reaction mixture. So for heating, okay. So we have to keep this solution until it starts to boil. So now it has almost heated, so we need to wait until bubbles start to come. So this is sufficient, so you can take the paper support like this and you can remove this solution from this electric stove. So after heating this solution near the boiling, so when the bubbles started to come, you have to remove and come back to this table, and you need to add stannous chloride in drop wise until the color of this solution becomes colorless, right? So you have to add the stannous chloride in hard condition only. Okay. So stannous chloride is a reducing agent. So when you add this, it will reduce ferric chloride to ferrous chloride. That is, Fe3 plus ions are reduced to Fe2 plus, so that's why the solution color will become colorless. So you have to add 2 more drops in order to ensure complete reduction. So 1 and 2 drops. Okay, so it will ensure complete reduction of the solution. And then, so you have to, after reducing, so you have to pour this reaction mixture by running tap water like this. Okay, through the walls of the conical flask, you have to run water so that it will be cooled. Okay. So now it has cooled to the room temperature. So you have to cool this to the room temperature before going to the next step. So after cooling, so you need to add 2 test tube of distilled water, right? So add 2 test tube of after this you need to add quarter test tube of, you can remove this, no need of this. So you need to add quarter test tube of mercury chloride in order to destroy excess stannous chloride which we have added. So we need to take a wax paper, right, and it should be cleaned, washed with the distilled water, and you have to place it on this white tile like this. Then you have to take the indicator droplets. Here the indicator, as already mentioned, is potassium ferricyanate. Indicator droplets on this wax paper, just like this. Okay, so take few drops. We have to go for the titration. Let us add, see, 1/4 of the mercury chloride in order to destroy excess stannous chloride. So I will take, so 1/4, that is up to this rubber band you have to add. Then so after adding this mercury chloride, you will get a very beautiful silky white PPT like this. So our next step is treating with potassium dichromate solution. It is an oxidizing agent. It will oxidize Fe2 plus to Fe3 plus, but stannous chloride, if it is there in the solution, what it will do, it is a reducing agent. It will reduce back Fe3 plus to Fe2 plus. Because of this, the amount of K2CO2 consumed will be more than the expected. Okay, so keep that in mind. So now we can go for this titration. So before going to start the titration, you have to take the indicator droplet like this, and you should keep ready this beaker containing tap water and a test tube containing distilled water and a glass rod. So first let us add around 7 ml. So and then we have to check. So after adding 7 ml only, we may have reached the end point. We will not be knowing because indicator is not there. So that's why first let us make a plan. So I will add up to 7 ml first. So just like this. This can be K2CO2 in solution, right? So if you are adding 7 ml, just take the solution, right? So start this addition and check whether we have reached the end point or what. So the way of checking is, you have to take the glass rod and it should be dipped in this test tube which is taken with the distilled water. So dip this glass rod into the reaction mixture and bring a drop of reaction mixture in contact with the first droplet of the indicator, just like this. So we are going to get a blue color. The indicator color will change into blue. So it is because this indicator is able to react with only Fe2 plus ions of the solution. If Fe2 plus ions are there, then only it is going to form an irreversible potassium ferroferricyanate complex, and that will be turnbull blue color in nature. So you are getting blue color like this if the reaction is not completed. If you are not reached the end point, you will get it. After adding 7 ml, so I will add 1 ml. So I will add up to 8, and now I will stop, because first titration is always a rough titration. Here we are going to get the range. See, before going to dip this glass rod, so make sure that the glass rod should be washed first with the tap water like this, and then it should be rinsed in the distilled water. So sometimes if you are not washing glass rod properly also, you are going to get a color. So dip this and bring it in contact with the second droplet of the indicator, right? So now let us see the color intensity of this indicator droplet is reduced from this drop to this drop. Go further, I will add 1 more ml, that is up to 9 ml. Okay. So again we may have reached the end point, so we have to check again and again. So wash the glass rod, rinse this distilled water and dip it in this solution and bring it in contact with the third droplet. Okay. So again it changes. So once again you have to continue the titration. Now added up to 10. Again we have to check. So like this. See, it is coming. Okay. So we need to add 1 more ml. That is up to 11. The glass properly, and then rinse it with this. Bring the reaction mixture in the same way into the next drop of the indicator. See, here you can observe the color intensity of this droplet is very light, right? this indicates that we are near the end point. So we'll add up to 12 now. Stop. So now we may have reached the end point. So that will be indicated by no change in the color of the indicator. The indicator droplet fails to turn to blue, then that is the indication of the end point. See here. So little bit color is changing again. So you can go 1 more ml, no problem. This time you can check. See, the indicator fails to change its color to blue color, right? So this indicates that there will be no Fe2 plus ions are there in the solution. All the Fe2 plus ions are oxidized to Fe3 plus ions. So you just have to note down this burette reading. So first trial you have to go for this. Final burette reading is 13 ml. Initial will be 0. So final minus initial is 13 ml. Now for the second trial, so I will refill the burette to 0, right? That is standard K2CO2 solution, and then I have pipetted out 25 ml of TMT bar solution. To that I have added 1/3 test tube of dilute HCl, then heated the solution near to boiling, and then in the hard condition I have added stannous chloride, right, until the color of the solution become colorless. After that I have added 2 more drops to ensure complete reduction, and then I have added 2 test tube of distilled water, and then so we need to add this mercury chloride into this, that is quarter test tube, so that we are going to get a silky white PPT like this. Okay, and then so we have to keep all these things ready, and then we have to start the titration. As for the first trial, we know the range, that is it comes at 13. So at 13 ml the indicator fails to change its color, so because of that reason now up to 12 we can add fast, right? We can straight away we can add up to 12, and after that we can go drop wise, that is for every 2 drops we have to stop and check in order to find out the accurate end point. 12, right? And then stir the solution like this. Okay, and now if you can touch this indicator droplet, see again it start to show the color change, that is it is changed to blue color. So now we have to go for drop wise, so that is for every 2 drops we have to check. So because we may have reached the end point here, and bring this. Okay, so still it is changing. After 12 we are doing like this. See, this reaction mixture and bring it in and to the next chart. So here, so if you feel if it is changing little bit, you can go further. Just we have to check whether we have reached the end point or what. So you can add 2 drops. See, indicator droplet fails to change its color, right? So that confirms the end point. So now this time very accurately we can get to know. So it is around 12.12, it is 12.3 ml, right? So in first trial we got the range. The first trial we got the range, that is 13. Now this is 12.3. 12.3 initially 0. This is 12.3. So similarly you have to go for third trial, right? Exactly in the same fashion you have to go for third trial. After completing the titration we will get the burette readings, concurrent burette readings. So the last step is now it is calibration part, right? So in the part A, so we have already taken the weight of the weighing bottle plus K2CO2 solution. It is M1. So it is 4.946. It comes this much, right? And then this weight of empty weighing bottle will be it is 3.685. Okay. So you have to subtract these two, and so that you will get weight of salt you have transferred, and that will be 1.261. Okay. Using this, you have to calculate the normality of K2CO2 207 solution. So substitute the weight of K2CR 207 you have taken. So that is 1.261. So that into 4 for 250 ml, and if you divide that with the equivalent weight, you are going to get the normality of K2CR 207, and that will be 0.1029. Okay, 0.1029. And then, so we have got the concordant value. The first trial we got 13, and then for the second and third trial we got 12.3. So as I have shown, right? So that concordant value we have to write, it is 12.3. Okay, and this is the weight of TMT bar that we are going to take it in 250 ml standard solution. So that is a given value, and it is 1.25 gram. Okay, so now using all these data we can easily calculate, and this is an approximation. So in the second part of the calculation, see, if 1000 ml of 1 normal K2CR 207, if it is much consisting of 55.85 gram of iron, then how much is for BML? B means that 12.3. BML of A normal. A normal means this normal of K2CR 207. So this is the question. So that's why if you want this much, you have to cross multiply. That means if you want BML of A normal K2CR 207 consists how much means you have to cross multiply this 55 into B into A divided by 1000 you have to do. So already this 1000 it is already converted into, after dividing it is converted to 0.05585 directly they have taken. So that's why you have to substitute the values here. So B value that comes for our experiment is 12.3 and A is 0.1029. So if you simplify this, we are going to get the values around 0.0706. Okay, we will get this. So this is the C value. It is for 25 ml of a TMT bar solution. So where C is, it is the amount of iron present in 25 ml of the TMT solution. So we have got this C for 25 ml of TMT, 25 ml of TMT solution. So to calculate it for 250 ml, we have to multiply with 10. So if you multiply, you are going to get D. So the D is 0. After multiplying this with 10, 0.706 it will come. Right now, in order to find out the percentage of iron present in the given TMT bar solution, you have to multiply this with 100. Right? Then you have to divide with the amount of TMT bar solution taken in the 250 ml. That is given value. That is how much? It is 1.25 grams. So if you do and simplify this, we are going to get 56.55 percentage. Okay, 55%. 56.55. So that's why the report is, it is the percentage of iron present in the given TMT bar solution is 56.55%. So this is the experiment. So thank you for listening. So happy learning.